Hi, welcome to week 6 of our MOOC on transport phenomena. Today we will look into unsteady heat transfer. Let me ask you the following question. Have you ever noticed that a metal object at room temperature feels cold when touched, while a wooden one of the same temperature feels warm? Why is that? Why are we so bad in measuring the temperature of an object? Sure, if the objects are very hot we will know, regardless if they are made of metal or wood. But isn't it strange that two objects that are of the same temperature can feel warm or cold? Why not both warm or both cold, depending on their temperature? The secret lies in heat transfer. Both the wooden and the metal are colder than our skin. Thus, there is a driving force for heat out of our hands. What we actually measure is the amount of heat leaving our hands. If that is large, we experience the object as cold. If it's small, the object feels like it is at the temperature of our skin, that is warm. The mechanism in both cases is conduction. In today's lecture, we will investigate what happens in the first instances. Our base case will be a thick, flat plate. It is initially at a uniform temperature T0. At some moment that we will call T is 0, the left side of the plate is set to a higher temperature T1. Obviously, we now have a driving temperature difference at the left side of the plate. Consequently, heat will flow into the plate. This heat will warm up the area close to the left boundary of the plate. While doing so, the flow will loosen its strength, as it leaves heat behind that is used to warm up the left part. So, eventually, all heat will be used and nothing is left that can further propagate into the plate. Thus, we may expect that the temperature close to the left boundary is higher than T0, while the rest of the plate hasn't changed its temperature at all. What will the temperature distribution look in the plate? Is it a straight line, such that the temperature T1 moves into the plate? Or is it a linear decrease towards T0 that we have seen in week 4 and 5? Neither of these two. It is a curved line that first drops fast, then bends over to gently connect to T0. In order to understand this, we set up a heat balance for a small strip in the plate. The strip is relatively close to the left. Heat will be flowing in from the left, as that part is warmer. Heat will flow out from the right, as that part is colder. But also, some heat will be left behind to warm up the strip, as eventually everything will be warmed up to a temperature T1. This is clearly an unsteady situation, with the ddt of E thermal larger than 0. The strip is warming up. Consequently, the heat flowing out is smaller than the heat flowing in. This also means that the further we go into the plate, the less heat is available for heating up. This causes the temperature profile to be curved, as we saw in the previous sheet. What drives this process? And what dictates how fast we heat up the plate? How large is the heat flux flowing into the plate? To answer these questions, we would have to construct a complete heat balance and solve it. This is mathematically difficult, but not impossible. However, we will not do it here, but instead be satisfied with a more qualitative understanding. Later on in this lecture, we will use the mathematical analysis for some exact formulation of key quantities. Obviously, the driving temperature difference T1 minus T0 plays a role. From the heat balance, we know that the thermal energy plays a crucial role. Thus, we can expect ρ times Cp of the strip to be important. The heat transport is via conduction. Thus, from Fourier's law, we know that lambda plays a role. Finally, the distance from the left hot interface must play a role, as well as time t itself. It turns out that lambda and rho Cp always occur in a fixed combination, lambda divided by rho Cp. This is denoted by the letter A, and it's called the thermal diffusivity. Actually, it is much like the ordinary diffusion coefficient from Fick's law, but now for diffusion of heat. It even has the same units, meters squared per second, as the diffusion coefficient. Do note, however, that it's lambda that needs to be used in Fourier's law, not A. Looking back, we see that we have 4 parameters that govern this problem, and that thus dictates the temperature change in the plate. We can perform a dimensional analysis on this problem, trying to find the temperature rise at position x at time t. The result would be that the temperature rise, normalized by the driving temperature difference T1 minus T0, is a function of only one parameter, namely x over the square root of A times T. What does this tell us? Well, take the temperature at a position x at time t. It has a certain value that we call T sub 2. Next, we look at a point that is twice as far from the left side, so at 2x. At what time would that point have a temperature T2? The dimensional analysis tells us that for a temperature T2, the ratio of x over the square root of AT must be the same value. Thus, we have for the original point that x over square root of AT must equal the ratio of the new point, 2x over square root of A times the unknown time. From this we easily see that the point 2x will have a temperature T2 4 times later. Thus, indeed, as we anticipated, the warming up of the plate goes slower when going deeper and deeper into the plate. So, we have a curved temperature profile that over time moves further and further into the plate, but at a slower pace when time increases. It is important to realize that our analysis assumes that the right-hand side of the plate is still at the original temperature T0. It has not yet changed its temperature. Obviously, at some point in time, the heat will also have reached the right-hand side and our analysis breaks down. We will deal with that in the next lecture. How far has the heat penetrated into the plate? That is given by what is called the penetration depth. It is given by the square root of pi times A times T. It tells us how far into the plate roughly the temperature has changed. Mathematically, it is found by taking the tangent to the temperature profile at the left-hand side and seeing where it cuts the x-axis, as is shown on the sheet. Also from the penetration depth, we see that the heating process slows down. The penetration depth moved inward not linear with time, but via its square root. From the definition of the penetration depth, we can also quickly calculate the heat flux into the plate that is flowing in at the left side. It is exactly equal to the ratio of lambda times the driving force divided by the penetration depth. This is not a surprise, as the heat flow is via conduction and thus via Fourier's law. The penetration depth is constructed such that the slope of the temperature at x equals 0 is exactly given by the driving temperature difference over the penetration depth. In the theory we discuss here, we have heat from one end penetrating into the plate. The other end did not notice yet. This theory of heat conduction into a flat plate is called penetration theory. It is valid as long as the heat is conducted from one side into a flat plate and the other end doesn't know yet. This can be put into a simple equation. Penetration theory holds as long as the penetration depth is smaller than half the thickness of the plate. After that, we enter into another regime. Penetration theory describes what happens in the first moment. Therefore, it's also referred to as short-time heat transfer. Notice that short times may to us feel long. Short doesn't refer to hours on the clock, but to the first part of the heating up of an object. We can of course write the flux to driving force relation also in terms of a heat transfer coefficient h, or preferably a Nusselt number. From the theory discussed here, Nusselt is a function of time, or written in its dimensionless form, Nusselt equals the square root of pi times the plate's thickness d squared over at. We can write the right-hand side using the Fourier number, FO. This number is defined as at over d squared. It gives the dimensionless time. We will come back to this number extensively in the next lecture. Let's look at the problem in the spark. You put a metal spoon in your hot soup, but got sidetracked. After how many minutes will the end of the spoon that you grab be so hot that you burn your fingers? Your silverware is probably made of stainless steel. So we look up the thermal diffusivity of stainless steel. It is 2.2 10 to the minus 5 meters squared per second. To be on the safe side, if you don't want to burn your fingers, take that the penetration depth is only halfway your spoon. From this, we compute that it takes about 80 seconds for the heat to reach halfway your spoon. The end is reached at 320 seconds, some 5 minutes. Thus, in between these two times, it becomes tricky picking up your spoon. Let's finally go back to our original question. Why does a metal object of room temperature feel cold and a wooden one warm? By now we can understand this. When you touch an object at room temperature, you basically put one side at a higher temperature. Metals will respond quickly. The heat flowing into the metal from your hand is at first governed by our penetration theory. The heat flux is large and your hand cools down. In the case of a wooden object, the penetration of heat is slow, as the penetration depth, being proportional to the square root of the thermal diffusivity, progresses slowly. Consequently, little heat flows into a wooden object, and your hand doesn't cool down at all, as your body can easily keep your skin now at a constant temperature. You experience this as if the wooden object is warm. How would this all work out if we had to deal with diffusion of mass? Well, not surprisingly, it is completely analogous. All we need to do is change A, the thermal diffusivity, to D, the diffusion coefficient. And of course, we need to talk about the mass flow rather than the heat flow. Other than that, everything stays the same. But do be careful with your notation. The D of plate's thickness and the D of diffusion coefficient should be clearly distinguished. Being sloppy with these makes that you calculate all kind of nonsense. One final word. We have discussed only warming up of an object. Luckily, cooling down, setting at T equals 0, the temperature of the left side to a lower value is also covered by what we discussed. All that happens is that the temperature profile is flipped along the x-axis and that now heat is flowing out of the plate. That's all for today's lecture. Try to repeat some of the derivations yourself and take a good look at the glass plate examples. Penetration theory is an easy yet powerful concept. Good luck until next lecture.